So a die could be loaded, and its probability of rolling a 6 is 3/6. Okay. So in contrast, if we have a fair die,
Yes.
then the probability of rolling a 6 or any of the other results is 1/6. So
Exactly.
this is an unfair die. This is a loaded die.
Yes.
Okay. So we have a loaded die. What else? What else is there in the example?
And let's say through some investigation that you have some prior knowledge about how dice are manufactured, and let's say that out of all the dice produced, 3% of them happen to be loaded.
Okay. So with prior knowledge, you learn that 3% of the dice are loaded. So we have a manufacturing process that manufactures these dice.
Yep.
And most of them are fair.
Yes.
97% of them are fair, but 3% of them have this defect, if you will. So they're 3% of them are loaded, and for these particular loaded dice, the probability of rolling a 6 is 3/6.
Yes.
Okay. So what's the question that we need to solve for this example?
So let's say we happen to have a die in our hand,
Uh-huh.
and we roll it, and we roll a 6.
Okay.
What is now the probability of this die being loaded, given that we rolled a 6?
Okay. So we take a given die and we roll a 6. So the question is, what is the probability that this die is loaded? That's the problem that we're going to solve. So we're going to use Bayes' theorem to solve this question, right? Okay, so let's do that. So Arnab, why don't you set up this problem in terms of Bayes' theorem for us?
Okay. So what is the probability of the die being loaded given that we rolled a 6? So using Bayes' theorem, that should be probability of rolling a 6 given that the die is loaded over probability of rolling a 6 given that it's loaded. And I forgot to write this down here. Probability of it being
loaded.
Okay. You guys can see that's a D over there.
Here. We'll rewrite this. It's okay. It's okay. Why don't you make sure that it's come over and make sure that you write it legibly. Yeah.
Loaded.
And this one.
Over here, loaded times the probability of just the die being loaded plus probability. So I'm just going to bring the denominator down here.
That's okay.
I can put in like a big bracket just in case of you guys. All right. The probability of rolling a 6 given that it's not loaded, or given that it's fair, let's use that. Times probability of being fair. Okay.
Right. Okay.
And then let me just close this guy off.
Okay. So I'm just gonna make sure that this is nice and legible here. This is loaded.
Yep.
Okay. Okay. All right. So we can now that we have Bayes' theorem stated for this particular problem, we can just fill in the numbers.
Yes.
Right? Okay. So
would you like to give it a try?
Yeah, why don't we do that? Okay. So we know that the probability of rolling a 6 for loaded die is 3 over 6.
Yep.
Okay. And the probability that the die is loaded is 3%. So 3 over 100. Okay. So that's the numerator. Okay, so that's the numerator. Now, the probability of rolling a 6, given that the die is loaded, times the probability that's loaded. So that's just the numerator again. 3 over 6 times 3 over 100 plus the probability of rolling a 6 when the die is fair. So we know that that's just 1 over 6 times the probability that the die is fair. So we know that that's 97 over 100.
Yes.
And that right there is the hard part, right? So yeah. we've now applied Bayes' theorem by plugging in the numbers into this formula here.
Yes.
Okay. So do you know what the answer is, by the way?
Yes. It is 0.085.
0.085. Or 8.5%. So if you roll a 6 from a randomly sampled batch of dice that you get from this manufacturing process,
yes,
then there is an 8.5% probability that the die is loaded.
Yes.
Okay.
This is our posterior probability.
Right.
What we have here is the prior probability, and with Bayes' theorem, applying all this together, so that gives you your posterior probability.
Right. So I think just to provide some context, when we say prior probability, we mean that before we collected any data, before we rolled any dice, we knew, based on our prior knowledge of the manufacturing process, that the probability of a die being loaded from this manufacturing process is 3%. So now that we've collected some data, now that we've actually rolled a die, we can calculate the probability that the die is loaded, given that we've actually collected that datum. Okay, so that's Bayes' theorem. So that's applying Bayes' theorem to a simple manufacturing process. Okay, so thank you very much, Arnab. I appreciate it. If you would like to learn more about statistics, chemistry, machine learning, or math, please visit my blog, The Chemical Statistician. You can also get more video tutorials on statistics and chemistry on my YouTube channel. You can also check out more episodes of the Central Equilibrium on my YouTube channel. And I'm very grateful for Arnab for being my guest today on the show. Thank you very much for watching this video, and I hope that you learned something useful today.